This experiment is entitled Equivalent Resistances. When you have completed this exercise, you will be able to determine the equivalent resistance for different combinations of series and parallel resistors. You will also be able to explain the concept of equivalent resistance using the information given in the exercise. Most electric circuits are made of different combinations of series and parallel resistors. The equivalent resistance of the complete circuit depends on the way the resistors are connected together. Resistors in series. When a group of resistors is connected in series, the total resistance is simply equal to the sum of the values of the resistor. If a resistor having a value of 5 ohm is connected series with one of 20 ohm, as shown in the figure, the total resistance between terminals A and B is 25 ohms. The two resistors could be replaced with a single resistor having an equivalent resistor equal to the value of R1 plus R2, which in this case is 25 ohms. The general formula for several resistors in series is R equation is equal to R1 plus R2 plus R3 plus R4 plus R sub n. Resistors in parallel. When two or more resistors are connected in parallel between two terminals, the resulting resistance is always less than that of the resistor having the lowest resistance. If as shown in the figure 1.7, the initial resistance between terminals A and B is changed by adding a 20 ohm resistor in parallel with a 5 ohm resistor. The opposition to current flow will be less than before. This is because the current now has an additional path to flow through, which was not available when the 5 ohm resistor was alone on the circuit. Electric current, like water, will flow through any path provided for it. When the resistor is connected across a power source, current will flow in the resistor. When a second resistor is connected in parallel with the first, additional current will flow, meaning that the effective resistance of the circuit has been reduced. If the second resistor is the same value as the first, the same amount of current will flow through each resistor. So the effect of adding a resistor of the same value is to double the current, or make the resistance half as weight. If a third equal resistor is now added, the current will be tripled, meaning that the equivalent resistor is only one-third of the original. This relationship is valid for any number of equal resistors. The formula for finding the equivalent resistance for a group of n resistors in parallel is 1 over Req is equal to 1 over R1 plus 1 over R2 plus 1 all over R3 plus 1 all over R4 plus 1 over R sub n, and so forth and so on. For the special case, when only two resistors are in parallel, the formula becomes R1 multiplied by R2 divided by R1 plus R2. Thus, 20 ohm in parallel with 5 ohm is equal to 4 ohm. Based on the discussion, we may now say that every circuit is the combination of the series and parallel combination of resistance. So therefore, in order to get the total value of any series parallel resistance circuit, is just we must apply the laws in adding series resistances and parallel resistances. After getting the total resistance, we may replace the resistance with its equivalent resistance. The resistive load module in the EMS system or lab vault consists of three identical sections, each having three resistors that can be added to a circuit using toggle switches. The selected value will appear across the output terminals of each section when the appropriate switches is closed, and any two or all three of the resistors can be placed in parallel. The equivalent parallel resistance will then be present across the output terminals. This resistors arrangement permits different values of resistance to be set, and a table giving many of the values can be found in Appendix B of this manual. The three sections of lab volt has 300 ohm, 600 ohm, and 1200 ohm resistance. As you can see, the longest length of metal in the case is the 1200 ohm, and the shortest is your 300 ohm. Getting the parallel combination of all these resistance, the equivalent resistance will be equal to 171 ohms. The first procedure in performing our experiment is to install the power supply, the AI, and resistive load module in the EMS workstation. Make sure the main power switch to the power supply is set to the off position and the voltage control knob is turned off fully counterclockwise. Ensure the power supply is connected to a three-phase wall receptacle. Ensure that the USB port cable from the computer is connected to the DI. Set up the series circuit as shown in this figure. Connect your DAE1 at circuit points A and B and use DAI I1 to measure the circuit current. Ensure that the correct polarities for voltage and current measurement are respected when connecting the DAI, and that the DAI low power input is connected to the main power supply. Next is to display the metering application and select Setup Configuration File ES11-2 DAI. Note that the metering setup configuration can be changed during the exercise if desired. So let us connect the circuit diagram shown in our lab module. So as you can see, I am connecting a series connection of your R1, R2, and R3. Taking note that the voltage that you would use is your 120 volts line voltage. Your R1 is consists of 171 ohm, your R2 is consists of 200 ohm, and your R3 has a value of 240 ohm. So your 171 ohm value will be the combination or the parallel combination of your 300 ohm, 1200 ohm, and your 600 ohm. The 200 ohm value at R2 is the combination of 600 and 300 ohm. Take note that is connected in parallel. Next is the parallel combination of your 1200 and 300 ohm. As you can see, the resistors are connected in series because the terminal 2 of your first resistor is connected to the terminal 1 of your second resistor, and the terminal 2 of your second resistor is connected to the terminal 1 of your third resistor. Take note that your R1 is equal to 171 ohm, your R2 is equal to 200 ohm, and your R3 is equal to 240 ohm. Next is our DAR or your data acquisition interface. Take note that the negative terminal of our ammeter is connected to the first terminal of our first resistor or terminal 1, in which it would be said that the ammeter is in series with the circuit. Next is our voltmeter. Take note that the voltmeter is connected in parallel with the total load. So as you can see, the first terminal or the positive terminal of our voltmeter is connected to the positive terminal of our ammeter, and the negative terminal of our voltmeter is connected to the N terminal of our source, which will measure the voltage of or the total voltage of the series resistance of the resistive load. And then, the positive terminal of our supply is connected to the positive terminal of our ammeter in order to give a positive current direction, and the neutral of our power supply is connected to the second terminal of our third resistor. To energize the circuit, let us now display our ES11-2 DAI. Note that this metering setup configuration can be changed during the exercise if desired. Turn on the main power supply, set the 24 volt AC power switch to the I position, and adjust the voltage control to 100%. From metering application, click the record data button to store the measurement of the circuit voltage and current in the data table. Turn off the power supply. Note that the values that will be measured by our ammeter and ohmmeter will be used in order solve for the resistance of the whole circuit, wherein we will use the equation V is equal to IR, wherein R is equal to V all over I. After getting the value of our voltage to our voltmeter and our current to our ammeter, then solving for the value of our resistance through the equation V is equal to IR, we may now verify if the value is approximately equal to the value that would be measured by our multimeter. After following the procedure of the first diagram, so let us now reconnect the circuit into our second diagram, which is the parallel combination of 300 ohm, 600 ohm, and 1200 ohm. As you can see, this is just a parallel combination of one branch of our love volt resistance. As you can see, this is our load, wherein our load is composed of the parallel combination of your 300 ohm, 600 ohm, and 1200 ohm. So as you can see, our voltmeter in our data acquisition interface is connected to the negative terminal of our ammeter, and its negative terminal is connected to the neutral of the source in order to measure the voltage of our load. Next is our ammeter is connected in series with our load. Since the positive terminal of our source is connected to the positive terminal of our ammeter, its negative terminal is connected directly to the load. Take note that an ammeter is always connected in series. In order to prove to you that the reading will just be the same, so I will reconnect the connections of our voltmeter, wherein our voltmeter will be cascaded directly to our load or parallel to our load. Therefore, I have removed my previous connection of my voltmeter and reconnect it, wherein my objective is to connect my voltmeter directly parallel to our load in order to measure the voltage that is coming from our supply to the load, or our load voltage. Let us now energize our circuit number 2. Like our previous procedure, we will display our ES11-2 and then turn our power supply into 100%. So as you can see, metering application will be paused, wherein we will have our voltage and current entering our load. Note, use these values in solving the value of your resistance, wherein V is equal to IR. So manipulate the equation into R is equal to V over I. In order to verify your calculations from our ammeter and voltmeter, let us read the resistance through our multimeter. So in order to verify the value of the resistance that you have computed from the reading of our meters, so let us turn off the power supply in order for us to use our multimeter in order to read the resistance in the parallel combinations of the resistors. Let's now connect our circuit diagram number 3. So let us set up this parallel circuit as shown in this figure. Connect the DAI E1 at circuits A and B and use DAI I1 to measure the circuit current. Ensure that the correct polarities are respected when connecting the DAI, and the DAI lower power input is connected in the main power supply. Take note that we will follow the line voltage 120 volts, therefore our R1 will be 171 ohm, or the combination of the three resistance, parallel combination of three resistance of each branch, and then your R2 is 300 ohms and our R3 is 600 ohms. As you can see, the resistance says of the two branches are in series, wherein our first branch or our first resistance is consists of three parallel resistors, which is 1, 2, 600 and 300, and our second resistance is the combination of the parallel resistance of 600 and 300 ohms. Then after that, we have connected our voltmeter in parallel with the series combination of the two, wherein the positive terminal is connected at the first terminal of our resistance 1, and the negative terminal is connected to the second terminal of our resistance 2. After getting the value of our voltage and our current, so let us manipulate those readings in order to solve for the value of resistance, and then let us verify it using our multimeter. Always make sure that the power supply is turned off or there's no power going to the resistance when you are getting the value of the resistances that are connected into the load. Let's now connect our circuit diagram number 4. Take note that our R1 is connected in parallel with the series combination of your R2 and R3, wherein your R1 at 120 volts will be equal to 300 ohms, and your R2 will be equal to 171 ohms, which is the parallel combinations of three resistances in a branch, and R3 is 200 ohms, which is a parallel combinations of 600 and 300 ohms. And take note that our voltmeter is in parallel with the combinations, and ammeter is of course in series with the circuit. Since the circuit is a parallel combination of your R1 to the series combination of R2 and R3, therefore we may say that the voltage of R1 is similar to the voltage of R2 plus R3. So therefore we may connect your voltmeter into the terminals of your R1, and knowing that the positive terminal of your E1 is connected to the positive terminal of your R1 and the negative terminal of your E1 is connected to the second terminal of your R1. And of course, your ammeter is connected in series with the circuit. Let us now energize the circuit. Always take note that the value that would be measured by our DI, by our voltmeter and our ammeter, will be used in getting the value of our load resistance. So using the formula V is equal to R, wherein your R is equal to V over I, we will have the value of the resistance of the load. So let us verify the reading of our voltmeter and our ammeter from our DI by multimeter resistance testing or reading. So when you are reading any circuit using your multimeter that is in resistance mode, always make sure that there is no power entering the load that you would want to measure. Like the other circuit diagrams that we have measured in this experiment, you would notice that the value of the resistance that is measured by our multimeter is approximately equal to the value of the resistance in the experiment using the DI and by calculations. Through this experiment, we have verified the validity of our Ohm's law and the equivalent resistance, your series and parallel resistances.